Hello, I'm going to go through the 2025 DCG higher level structural forms question from 2025 in this video. I hope it'll be helpful, particularly for the students on PN4036 module that I'm leading at UL. So first up, we just look at the question here. This figure here below shows the elevation plan and in view of a kicking T in the form of a hyperboloid of revolution. What they're asking in the question is to draw the given plan and elevation of the kicking T, and then project the given end view and determine the position of the directrix and the focal point for one branch of the double hyperbola in elevation. So pretty straightforward. What you need to know before we start is the basic principles on the hyperbola. You need to understand the whole idea of a throat circle and your base circle in the hyperbola. The hyperboloid of revolution. And yes, we can go from there. So if I just show you in the DCG book, having an understanding of the different methods of drawing the hyperboloid of revolution will be a good starting point. And also to understand, in this question here, that I've used the asymptote method, and to understand what the asymptotes are. So if we here look at in this question here, we can see the asymptote is basically, it's a true length element that can be found on your hyperboloid of revolution, and it's a true length because it is parallel with the vertical plane of reference, or it's a horizontal line here in plan view. And so therefore, if it's a horizontal line in plan view, or more specifically, if it's parallel to the XY line, it is going to be a true length line. We look at it here in elevation. So that's key to that there as well. So to show you, so this is the solution for the question. So while this is quite packed looking here, I think it's pretty straightforward just to show you. So we have the question here. So 55 millimeters up is the distance from the base circle to the throat circle, which you can see here. And it's also given in the question then with 104 is the base and 50 for the throat. So we can see that there 104 is your base, and your throat circle here in the center is 50 millimeters. So that's all good there. So what I've done essentially for this here is you can see that I have the outline of a hyperbola here, left and right. So that's the first thing that you're going to have to construct in terms of just your light construction. And you'll see, so we'll draw that in plan view as well. So very straightforward to draw this here in plan view. So the 104 and the 50. This elliptical shape is not possible to draw straight away because that's due to the cut surface. So that can be looked at again shortly. But in terms of, I can make that throat circle there just a little bit thicker so you can see it. There we go. You can see the throat circle there in plan view as well. I use the asymptote method, and what that essentially is where we break up our asymptote here into just half of the asymptote into an equal number of parts. And what we do then is we find, so we basically rotate each of those points on the asymptotes around until they meet our axis here. So for example, if I look here at an easy one to look at is number 3. So number 3 in plan is going to roll around until it meets the axis of the circle, and from here brought straight up. And when we bring it straight up all the way here, you can see that this is going to map onto our point 3, but it's very important here as well that we realize where does this horizontal line come from, and that horizontal line comes from the original point here, which is 3 as well. So you can see this. So if I just extend that up there, So here is, you're just rolling your point around the hyperboloid of revolution. You're rolling it around an imaginary circle which stays horizontal. And so as a result, this arc is produced. But because we're rolling it around, we know that point 3 is going to be up here. It's on the asymptote here, and we just move it across, and that's going to give us our point 3 here on the actual hyperbola that's going to be generated. So yeah, so hopefully that's helpful there with that. So the same is going to be for 0, 1, 2, 3, 4, points 1, 2, 3, and 4. Point 0, which is point 0 is going to be straightforward. It just rolls around the throat circle, so it's going to be that quadrant there in the throat circle, which is going to give us that there. So that's all straightforward. And what that does is it gives you one branch. When you join those points together, it gives you half of the branch, basically. And all I've done here using CAD is I've just mirrored that half around up there. If you're doing manual drafting, you're going to have to use axial symmetry in order to do that, or you could potentially use a template for it there. So once you have the branch done on the right hand side, it's just mirrored across the axis of the hyperboloid to find the same branch on the left hand side. So that is done. The other thing then is similarly in elevation, because when you look at the hyperboloid of revolution, so if I just show you here, I also have a SolidWorks model of it made. Just roll this back a small bit. So when you look at your hyperboloid of revolution, forgive all the construction lines you can see here, but no matter what, it's a symmetrical figure, so it's going to look the same in any elevation view. It's always going to look the same. So in the elevation, so all good auxiliary elevations. So that is that. So you can draw the outline of your in view here also as well. The next part of the question is a tricky question. So, okay, if we're still in part A, what we have to do is we have to create this cut at 30 degrees. And that's straightforward enough to draw in that line there from the vertex of the hyperbola, drawing a line that's 30 degrees. So to show you there, very straightforward. So that line there is 30 degrees, just like that there. And what that does is it cuts the hyperboloid of revolution at this point and also at this point up here. We can find those 2 points in plan view. They're going to be on the axis in plan view. So we have this point here, straightforward, and we also have another point here down below here, which is straightforward. Now, the next part of the question is a little bit tricky. I'm going to show how it's done. The principle that you have to understand for this here is this whole idea of, so here's our cone, here's our hyperboloid revolution. Let me just hide some of the sketches there. Easier. Okay, so the next part is, what I'm going to do is we take a series of cuts, right? So if we take a series of horizontal cuts along this cut section here, any horizontal cut in a hyperboloid of revolution is always going to give us a circle. So for example, let me just suppress this here. And what you can see there is when I cut the hyperboloid of revolution across using a horizontal cut, that horizontal cut is actually creating a circle. So there's an infinite amount of circles here. If I unsuppress this now. All right. So what we do in this question is we can take a number of horizontal cuts. In this, I've taken an even number. The less you can take, the better, but you still have to be able to construct an ellipse here. So if you imagine this circle here, and when we look at this circle now in plan view, we can see that that circle cuts the ellipse in two different parts here, right? So it cuts it here and cuts it here. So using that principle, what we can do is apply the same principle here. So for example, I'm going to just deal with this cut section here, right? So just from here across. So we know that that cut section, so this distance that I'm showing with my cursor is the radius of a circle. And so for now, let me just draw in the circle. Now just let me draw in a circle here that I'm going to just use as a reference. Now the circle is actually flat, right? So we're just drawing it here. So the circle is actually like this here, it's flat. But that is useful now, this what I just have here. And what I'm going to do is I'll just draw a line across here. So just to remind myself about it. And we'll take this circle down to plan now so we can see this in plan view. So when I take it down to plan and just land in the center here, so that's the circle now that I'm concerned about. So that is the plan view of this circle that goes all the way across here through this section. And the key thing that we're concerned about here is not this point here. We're concerned about where the circle cuts this line, right? And what that line is that we're looking at is this point here and this point here. So that's where it cuts. So what I'll just highlight here again, just for now, is I'll just drop this here so you can see it. So that's where it cuts. We know it cuts it in 2 points. And when I come down here now, you can see that this is my original circle. This is 1 point where it cut, and the other point where it cuts down here. And when we repeat that same process, we'll plot enough points that we can then draw in this ellipse, which I'm highlighting here now. I'll just change it to red for now. We're drawing in that ellipse there. So that's how you construct your the shape of the cut section in plan view, taking those series of horizontal cuts. So you'll see in my question, what I've done for this particular one here is I have divided this overall height from here. So in terms of looking at the height from this height to this height here into 4 equal spaces. You could go 6, 8, whatever you want. And the beauty about dividing it into an even number of spaces is that that will then the central point in that line then will be the center of the ellipse in plan view. So if I just show you here, that's going to be an ellipse here, and that's going to be the center line, central axis of our ellipse down here. So that is that. So using that method, you should be able to then construct ellipse in plan view. And just to remind you, the key is that you need to take horizontal cuts. You need to bring your circle, the radius here, whatever the radius is that you create, down to plan view, and then drop your line from where it cuts the cut surface, and then you'll find your corresponding points in plan view. So you'll be able to figure that out looking at the handout that I'll give you in the lecture. So that is that. And then the last part, just to complete the end elevation here, is pretty straightforward. I know that the top of my ellipse is along this line. I know that the bottom of my ellipse is along a line. I'll just show you here, a construction line just right across here. So determined by this point here, straight across. So that's that. And then, so we have the top and we have the bottom. And the other thing then is the left and right, the vertices. So we get those by just bringing them across. We know that this is the center line of our ellipse here. So bring this line straight across, convert it, and project it all the way up here to your end elevation there as well. And obviously it's going to be across on that central line just there. So that'll give you your 4 points of your ellipse. If you can do that, it's manual drafting. You're going to have to maybe use a template or whatever. Using AutoCAD is pretty straightforward. Just you have axis, and then another top or bottom of this axis here. So that is that. And just the last part of the question is determine the position of the directrix and the focal point for one branch of the double hyperbola in elevation. In order to do this, you just need to have a little bit of need to have an understanding of the principles of a hyperbola. So I'd revert you back here to conic sections. It would be a good place to start. And if you just look here in conic sections, let me see. Yeah, this is a nice one to use here. So in order to draw the directrix, the directrix is pretty straightforward. So see here. Yeah. So in order to draw the directrix, again, it can be sometimes a little bit tricky to unpack this, but you can see here, if we draw a circle, which is the diameter of this transverse axis between our two vertices, and where that circle cuts the asymptotes, the point of intersection between the circle and the asymptote is going to give us a point on 2 points in our directrix. So that's what I've done here. So I've drawn in this circle here, which is the length of the transverse axis, and you can then see where that circle cut the asymptote here. So these are our asymptotes here that I've drawn in. Where they cut the asymptotes, that's going to give us a point, 2 points in our directrix here and here. We have a directrix on the other side as well, but you don't need to draw in both of them. And just to remind you, where did we get the asymptote here? The asymptote is basically this line here, all the way across. So that line from there to there in plan view, and projecting your points up. And so one line on the asymptote is on the base circle, and the other line on the asymptote is on the, if I just extend that up there, the other one is directly up there like that. Okay, so that's how you do that. So that should be hopefully straightforward there. So that's the directrix drawn in, and the other one then is the focal point for one branch of the hyperbola. So if you look here, I've shown two ways in this question, again, back to simple principles. If you go from where this circle, the auxiliary circle, cuts the asymptote, if we go 90 degrees from that towards the axis, we'll find the focal point. Or alternatively, what you can do is from the center here, where the a line drawn straight up from the vertex, where that hits the asymptote, we can roll it. We can roll back down this way here. So I'll just show you the two methods here. It's going to give the same result for both of them. So this first line that I've drawn in here, where the asymptote and the directrix meet, a line drawn perpendicular to the asymptote there, like this here. If I just show you that angle there is 90 degrees, that is going to give you where that passes through the axis, that's your focus there. And alternatively, you can see here where I've drawn up this line here. This is just another method. You can verify this way as well. Vertical line straight up here, or a line parallel to the axis of the hyperboloid revolution, where that line from the vertex cuts the asymptote. We can then roll that down, and you can see there, when you roll it down, that's going to, where that line arc rolls and hits the axis, that's going to give you a focal point. So you can see there I have the exact same point for both of them. So that's it. That's the question. Tricky enough. You'd need to know your stuff in relation to just the principles of a hyperbola here. So that would be really important for that one. And the other kind of key to the question is really about understanding horizontal sections of a hyperboloid of revolution always produce a circle, and what you're doing here is you're generating a number of horizontal cuts, you're finding the associated circle in plan view, and you're just mapping your points then, and you can then create your cut section here. So just remember then, also, it's always a pure ellipse that's drawn here in elevation. So if I was to show you draw, see here, if I was to draw just on the front plane here, a line, if I was to draw a line from here down as far as here, you can see 74.9 millimeters to one decimal place, 74.9. And if I show you here on my AutoCAD, when I did it in 2D, if I just measure that line now, that line there, you can see 74.88. All right, so that's that. But what that creates is it creates I look at that surface now. If I look at that perpendicularly, that surface is always an ellipse, and they are just versions of that ellipse. Then when we look at it in plan view, it's also going to be an ellipse, and then when we look at it in end view, it's going to be an ellipse there as well. Obviously not the true shape of the cut surface, but it's the projection of the ellipse is always going to be an ellipse as well. All right, so that's it. I hope that that's helpful. Just, I suppose, if I just want to go back and just show you what I did in terms of constructing the hyperboloid of revolution. I started off just with, see there, you can see my asymptote that I've drawn there. I just did some constructions up here. It's not straightforward to do it in SolidWorks. So what you can see there is I generated a series of generators here, or elements. Again, if you want to look in the book here, structural forms, you can see there that it, like, if you look at the so this method here, so we could call it the elements method. So that's essentially what you're looking at here, where all of those elements that I've drawn, you look at it here, they're all tangential. All of those elements are all tangential to the throat circle. So every one of those are tangential to the throat circle. And the more elements you have, the accurate it'll be. So when I look at that now in elevation, I can see a kind of a vague outline of a hyperbola, but it wouldn't be enough to generate a nice smooth one. So what I did, just to kind of speed things up for me just a little bit, and there'd be other ways to do this in SolidWorks, so this is not the only way to do it. I just created a 2D sketch because I had my vertices, I had my top and my bottom, and what I was able to do then was I was able to produce, so here, so I was able to generate a sketch of a hyperbola, or just using a spline. And where that method came from here is this very simple one here in the book, the rectangle method. So I was just able to plot it that way. And once I had that done, I was just able to revolve it. So I was able to just create a sketch here of the hyperbola, and I just revolved that shape then, what you can see there, about the central axis, and that gave me really nice hyperboloid of revolution. And all I did then was I just cut, so I just looked in at it here in elevation and just cut it with a line, and yeah, so, and then you can see the circle there afterwards. And just to kind of, to make that a little bit quieter, you can just hide everything there, and just roll back. So SolidWorks is useful. It's not very straightforward, but again, it does offer us a little bit more in terms of visualization, and it helps to make sense of what we do here two-dimensionally. So I hope that's helpful.